Hello students, I welcome you all to my channel Engineers Academy. Do hit the subscribe button if you haven't done it yet. Now we are going to solve this problem which says that the young tree originally bent has been brought into the vertical position by adjusting the three guy wire tensions to AB equals to 0, AC equals to 10 pounds and AD equals to 15 pounds. Determine the force and moment reactions at the trunk base point O. Neglect the weight of the tree. So the tension in this AB cable is 0 and the tension in this AC is 10 pound and the tension in AD is 15 pound. So we have to find the reaction forces at O. So we have to find OX, OY and OZ, and we have to find the moments at O. So that will be moment at O. So that is MOX, MOY and MOZ. So we will have the forces, the tensions in the ropes in this direction. So let's say this is my tension AD. This has a magnitude of, AC has a magnitude of 10 pounds and AD has a magnitude of 15 pounds. And let's say that the reactions at O is, let's say this is OX, which is acting in the positive X. Let's say we have OY and OZ is acting in the upward direction. This is OZ. And we will have the moments as well. So the moments about O is MOX. This will be MOY. And here we will have MOZ. And all these moments are the positive moments. These are the counterclockwise moment. If we curl our right hand fingers in the direction of MOX, so it is pointing out in the X direction, so it is the counterclockwise moment about X. And similarly about MOY and MOZ. Now to solve this problem, first of all we have to represent these tensions as a Cartesian vector. So we have to write the tension from A to C is, we have to represent that as TAC vector, and this TAC vector will be equal to its magnitude times the unit vector. So TAC tension has a magnitude of 10 pounds, so its magnitude is 10, and we have to find out the unit vector from A to C since it is acting from A to C. So we can write that this is 10 multiplied by, the unit vector from A to C is the position vector from A to C and divided by the magnitude of that position vector. So now this is 10, and now the position vector from A to C, to find the position vector from A to C we need to travel 5 feet in the negative Z direction. Then we have to travel, from this we have to travel we have to travel 5 feet in the negative Z, then we have to travel 5 feet in the positive Y, and then we have to travel 3 feet in the positive X. This is 3 feet, this is 5. So we will have the position vector, so we will have minus 5k, that is in the negative k we have to travel 5 feet, then we have to travel 5 feet in the positive j, so I will write plus 5j, and then from there we have to travel 3 feet in the positive I, that is in the positive X, so plus 3I. So this is the position vector from A to C, and now its magnitude will be, we have to take the squares of each component, that is 3 square plus 5 square plus 5 square under the square root. So this will give us the magnitude of the position vector from A to C. So this is 3 square plus 5 square plus 5 square. This gives us 7.681. So this is approximately equal to 7.681, and the units will be in feet. So now we can write that the tension from A to C as a Cartesian vector is equal to, now we can divide, we need to divide each component by this magnitude. So we can write this as 10, and this will be 3 divided by 7.681 I plus 5 divided by 7.681 j and minus 5 divided by 7.681 k. And further we can multiply this 10 inside with each component, right? So if I multiply this 10 with 3, so it will become 30, and this will become 50, and this will become 50. So let me write it as this will become 30, 50 and this is minus 50. Now let's find all these components. So 30 divided by 7.681, this gives us 3.906. so this is 3.906i, and this is TAC Cartesian vector. And then we have 50 divided by 7.681, this gives me 6.509. so we can say that this is approximately 6.510. this is J, and this will be minus 6.510 K. So this is the Cartesian vector for the tension in AC cable. Similarly, we can find the tension, the Cartesian vector representation of the tension in AD cable. So now we can write that again the magnitude of that TAD is given. This is 15. So we will write that this is 15 times the unit vector from A to D. And we can write that the unit vector from A to D is the position vector from A to D divided by its magnitude. And now to find the position vector from A to D, again we need to travel 5 feet in the negative K. So I will write minus 5K, and then from there we need to travel 5 feet in the positive Y, so plus 5J. And then from there, when we reach here, then we need to travel 3 feet in the negative X direction. So I will write minus 3, that is minus 3I. And if we find the magnitude, so that will be 3 square plus 5 square plus 5 square under the square root. So we will get that same magnitude, which is 7.681. This magnitude is not 10, this is 15, right? So this is 15, this is not 10. So then we have to write this as 15 and this is 15. So now we can multiply this 15, this 15. So this is 15 minus 15 into 3 divided by that magnitude, which is 7.681 into I. Then we will have plus 15 into 5 divided by 7.681J, and then minus 15 into 5 divided by 7.681K. So now let's find all these. This is 15 multiplied by 3 divided by 7.681. This gives us 5.859I. Similarly, 15 multiplied by 5 divided by 7.681. This gives us 9.764J, and then minus 9.764K. So this is the Cartesian vector representation of the tension in that AD cable. And similarly, it is said that the tension in AB cable is 0, so we can write that TAB is 0I plus 0J plus 0K. So it's a 0 vector. Now to find that OX, OY, the reactions at O, this OX, OY and OZ, we have to apply the summation of forces along X, Y and Z. Since this tree is in equilibrium, so we will write that the summation of forces along X is equals to 0. So first of all, we have this OX in the X direction, so I will write OX. And then we have to add up all the I components, that is the X component of this TAC, the X component of TAD, and the X component of AB. So this will be plus 3.906. Let me write only the magnitude. This is 3.906, then 5 plus 5 and sorry, this is not plus, this is negative. Since we have minus sign here, so this is negative. So let's write this is minus. So this is minus 5.859, and this is 0. So we will write plus 0. This is equal to 0. And from this we can write that OX is equal to, if we bring these two terms to the other side, so their signs will become opposite. So we will have 5.859 minus 3.906. So from this, OX is equal to 5.859 minus 3.906. This gives me 1.953, 1.953, and this will be in pounds. So this is OX. Similarly, if we if we apply the summation of forces along the y direction, that will be equal to 0. So again we have this OY, so I will write OY. Then we will have this plus 6.510, and then we have this 9.764 plus 9.764, and then we have this 0. So this will be equal to 0, and from this we can write that OY equals to minus 6.510 minus 9.764. So this is minus 6.510 minus 7.764. This gives me OY equals to minus 16.274 pounds. So this means that the assumed direction of OY is not accurate. OY is acting in the opposite direction. OY is acting in the negative y direction. Similarly, to find OZ, we have to apply the summation of forces along Z equals to 0. And then we have to write that this OZ is acting in the positive Z. So I will write OZ. Then we will add the K components. This is minus 6.510. And then we have this minus 9.764, and then this 0. So this is plus 0. This will be equal to 0, and from this we can write that OZ is equal to OY, but it is acting in the, but we will have the sum equals to plus 16.274 pounds. So this is OZ. Now to find the moments, reactions, that is MOX, MOY and MOZ, we have to apply we have to find the moment at point O equals to 0. So let me apply the summation of the moment about point O, that will be equal to 0. So we have to find the moment of each tension, right? So we will write that this, we can write this MOX, MOY and MOZ as a resultant moment. So that resultant moment will be equal to MO as a vector, that will be MOX I plus MOY J plus MOZ K. And then we have to find the moment of this tension in AD and tension in AC. So we will write that MO, this MO plus the moment of that AD, that is the tension in AD, and plus the moment due to the tension in AC, this will be equal to 0. So now MO, this is MO, we will write this as MOX I plus MOYJ plus MOZK. And now for the moment of TAD, that is the tension in AD, we have to find the moment arm. We have to decide the position vector. So we can decide the position vector, we can select the position vector from O to A. So that will be the moment arm for the tension in AD. And similarly, the same position vector, that is the position vector from O to A, can be selected as the moment arm for this TAC as well. So let me write that this will be the position vector from O to A cross TAD vector plus the position vector from O to A cross TAC vector. So this is equal to 0. So MOXI plus MOYJ plus MOZK. And then we have to find these moments. So this is I, J and K. And the position vector from O to A, the position vector from O to A is plus 5K only, right? So let me write that the position vector from O to A, which is the moment arm for both the tensions, this is 0I plus 0J plus 5K. So we will write this as 0I plus 0J plus 5k. And similarly the tension from A to D, this is the components of the tension from A to D. This is minus 5.859, minus 5.859, then this is plus 9.764, and then we will have minus 9.764, minus 9.764, and then plus, and the moment of the tension in AC, so that is I, J and K, and this is 0, 0 plus 5, and TAC is, for TAC we have to write 3.906, 3.906, and then this 9 points, this is 6.510, 6.510, and minus 6.510. So this is equal to 0. So we will have the same moment about point O plus. Now let's find all these. So first of all we will have this. So this is plus I, and this minus this. So this is minus 5 into 9.764, and then we will have this for J, and with J we need to write minus. So this is 0 minus this, so minus 5 into minus 5.859, and then for K, that is plus K, and this will become 0 minus 0. So with K we will have 0. So this is 0K. This is plus 0K. Similarly we can find, now first let me find all these products. Like first let me find this. This is minus 5 into 9.764. So this is minus 48. This is minus 48.82i. Similarly that is minus 5. This minus into minus is minus, and minus, this minus into minus is plus, and plus into minus is minus. So we will write minus, this is minus, and then 5 into 5.859. So this gives me 29.295 and plus 0K. So this is the moment due to the tension in AD. This is the moment due to the tension in AD. Similarly we will write plus, and now the moment due to the tension in AC. So that is, again we will write this like this, and this will be plus I, and this will be 0 minus this. So this is minus 5 into 6.510, and then the second column. So for the second column this is 0 minus this, and with J we need to write minus. So this is minus in minus 5, sorry, this is this will be minus, and minus 5 into 3.906, and similarly for K this will become 0 and 0. So this is 0K. So this is plus 0K. So now first let's find all these. This is minus 5 into 6.510. This gives me 32.55. So this is minus, and this will become minus into minus is plus, and minus into minus is plus. So we will write plus, and this is 5 multiplied by 3.906. This gives me 19.53. This is 19.53J and plus 0K, and this whole will be equal to 0. So now we have to add up all the x components, that is the summation of the moment about x equals to 0. So we will add up all the x components. So this is MOX. So MOX and then this minus 48.82, and then this component, this is minus 32.55 minus, this is equal to 0, and the other, on the other side of equation, both of these terms will become positive, so we can write this as like this. So we will have MOX equal to the summation of both of these. So this is 48.82 plus 32.55. This gives me MOX equals to 81.37, and this will be pound feet. Similarly, we will apply the summation of the moment about y equals to 0. Now we have to add up all the y component. This is MOY, so we will write MOY, and then this y component, this is minus 29.295 j, and then we have this j component, which is 19.53, so plus 19.53, and this will be equal to 0. So we can write that MOY is equal to plus 2.9295 minus, this is plus 29.295 minus 19.53. So 29.295 minus 19.53, this gives me MOY equals to 9.765 pound feet. And similarly, to find the moment about the reaction of the moment about the z-axis, so we have to find this sum equals to 0. So we have to write MOZ, this MOZ plus this 0 plus this 0. So this means that MOZ is equal to 0. So the reaction moment at O along x is 81.37 pound feet, and the reaction moment at O along the y direction is 9.765, and the reaction moment about the z-axis is 0, and the reaction forces at O along the x is 1.953 pounds, along the y is minus 16.274, so the minus sign tells us that it is acting in the negative y, and the reaction force along the z is 16.274. So this is the solution of this particular problem. I hope this will help you in your learning.